Okay, we will continue with question 20. So if you look at this graph, it is temperature and time. So basically, just by looking at this graph, you need to have the understanding that the gradient of each line will actually give you the rate of temperature change over time. Now this understanding is very important, and I will highlight that importance later. The second thing that you need to take note is this statement that P and Q are heated at the same power. Okay, and power is equals to E over T, meaning that if we divide the energy by time, the power of P and the power of Q will be the same. And we need to make use of this information later in our calculation. Okay, so let's start tackling this question. So just by looking at this question, we should have an idea that it is about heat capacities and things like that. So I decided to try it out. So I write down the formula, E equals to mc delta T. And then I realized that this E, if we divide this equation by time on both sides, we should see something happening. So if I take the left hand side and I divide it by time, I will get E over T. And E over T is actually your power. So I know that it is approaching the right track. And then on the right hand side, because left hand side I divide by time, the right hand side I must divide by time as well. So mc delta T, and if I divide it by time, I notice that, oh, I see this quantity here. And this quantity actually is represented by the gradient of the graph. So I know that, oh, okay, it kind of looks like I have used the right approach. So if I simplify this equation, on the left hand side it will become power, and it will be equals to mc delta temperature over time, and this one is actually the gradient of each line. Okay, so knowing that I need to make use of the gradient of the P and Q line, I proceed to calculate the gradient of the line. So this is the gradient of the line, 7.5 and 5. Then after that, I make use of the information that the power must be the same. So on the left hand side will be the power for P, and the power for P is actually given by this equation here, right? So it will be the mass of P times the capacity of P, then the gradient of P. And then the right hand side similarly, but is for Q. So once I have that, because P and Q are of the same material, they are of copper, so meaning that the heat capacity, which is only dependent on the material, P and Q's heat capacity must be the same. So because of that, Cp and Cq, I can cancel it on both sides. So I'm left with Mp and the gradient of P, which is 7.5, equals to mass of Q and the gradient of Q. Okay, and the question actually asks you for the ratio of the mass P to the ratio to that of Q. So meaning that I have to find out the value of MP over MQ. So just by doing some manipulation, I will get the number 2 over 3. Now this question will be a little bit difficult if your mathematics is not that strong. So for students who are still not clear about this working, please come and approach me and I will explain to you. I will break it down into smaller steps for you. Okay, question 21 is about waveform. Okay, so they tell you that an oscillation is made once every 4 seconds. Okay, so this one would tell you the period of the wave. Then after that, they ask you to predict the shape of the spring 2 seconds later. So you know that one complete oscillation takes 4 seconds. So if you are only looking at 2 seconds later, it means that it must have moved half a wavelength, right? So if you look at this diagram, this is the initial wave. So if I take the starting point here, this is my starting point. Basically, after 2 seconds later, this starting point would have moved half a wavelength away. But of course, you need to take note that the particles at this point is actually oscillating up and down. It doesn't move left and right. What I'm doing is that I know that, okay, this guy is going to go up down, up, normal, down, normal, up. Right? So if I have the understanding, basically if I shift this to half a wavelength, that means my wave would actually be like this. So please remember that this point does not move to the right. It is actually oscillating up and down, up and down, up and down, up and down. What I'm saying is that half a wave, to move a complete wavelength, it will be up, middle, down, middle, up. So if I move half a wavelength, it will be, okay, write down, for a full wavelength, it will be up, middle, down, middle, up. So this point is oscillating up, middle, down, middle, up. This is one full oscillation. Okay, so meaning that if you are doing half an oscillation, it will be at up, middle, down. Okay, meaning that this point will be at here 2 seconds later. So if you draw this line and you link up with all the rest, you will see that the wave actually looks like this. Let me use a red pen, so it will look like this. So something that looks like B. Okay, so that is how you deduce the answer. Now some of you may be wondering, how come before you write this down, I already start sketching the wave like this? Now the thing is that there are different approaches to this question. Initially I was thinking that maybe I can tell you that, okay, imagine the wave start doing a phase shifting of half a wavelength, and then you can backtrack and then draw this thing out. That is one approach as well, but I'm afraid that if I use that approach, you may think that this particle is actually moving to the right, and that is actually wrong. Particles on the wave is actually oscillating about its own fixed position. So if this is a spring and you are waving it, actually the particle here is actually just moving up and down. It's not moving to the right. So that's why before I go into that first approach, I decided, okay, maybe I will just write down the up, middle, down, middle, up, and then break it down for you. Okay. If you are still not clear about this, do approach me. It is not a question that you can easily visualize it. Okay. So remember, one for oscillation is always up, middle, down, middle, up, because you have to return to that position to be considered as one complete oscillation. So 4 seconds is for one complete one. So 2 seconds means that you only do it halfway. So the halfway point is this down thing, right? So that's why this particle will be at the down position 2 seconds later. So if you do it for every point, you will realize that you can trace this red line out. Okay? Okay, question 22. Question 22, you need to draw the light ray out before you can answer the question. Now to draw this light ray, the trick is that you should start by drawing out the image of each point. So let me redo the thing so that you can see how I got the answer. So I'm going to erase the line. Some of the line. So what I do is that, let's say P, I will just extend the mirror, it's alright, no issue. Okay, this is just a reference line for you. Okay, you cannot physically stretch the mirror out, but you can just extend this line out, taking it as a reference because you want to measure the object distance so that you can locate the image. So first locate the image of P, Q, and R. Then from here, from the image, draw a straight line to your point E, which is actually your eyes. So from here, you notice that I only start drawing solid line, on the top side of the mirror, because that is how the light ray is going to bounce. Okay, so it will bounce at this point. Then after that, at the intersection point between the mirror boundary and the light ray that you draw, you connect it with the object itself. So this way you do not need to use your projector, and you do not need to draw the normal to ensure that your angle of incident and the angle of reflection is the same. You can tell that using this method, you are going to get the law of reflection considered already. So by drawing this, you will see that as this obstacle is moving down, the first light ray that is going to cut is the light ray coming from object P. So that's why object P will disappear first, and as it moves down, the last ray that is going to block is the ray from R. So that's why R will disappear last. Okay. Question 23. Common mistake is that students directly use the value 40 and 120 in their Snell's laws calculation. So down here, the light is actually traveling from glass to air. From glass to air, you cannot use n equals to sine I over sine R, because that short form is only applicable for light rays coming in from optically less dense to an optically denser area. So you cannot use your n equals to sine I over sine R here. Instead, you have to use the Snell's law. That means the original Snell's law. Original Snell's law states that is sine theta 1 n 1 equals to sine theta 2 n 2. And in class, I have always tried to convince you to use this approach, and it is very simple. Just treat all the values here to be the property of those things in the class. Okay, so in here on the left hand side, I have to find out what is the angle between the ray and the normal. So here 120 minus 90, you get 30 degrees. So on the left hand side will be all the parameters from the glass. So the angle in the glass is 30 degree, and of course, because I have already said, right, the left hand side will be all the property of glass. So this refractive index is of the glass one. Then on the right hand side is everything for the air. All the parameters are those that in the air boundary one. So from here, I have to find out what is the angle here again between the ray and the normal. You notice that I didn't use the word incident or refraction, because when you are using the original form of the Snell's law, there is no consideration of the direction of the light. So it's not like on the left hand side it must always be the incident, or on the right hand side must always be the refraction. It does not matter. It does not work that way. Okay, to Snell's law, it is just a ratio. Okay, so I will continue on the right side. I will just put all the parameters that I get from the air boundary side. So the angle here will be 50 degree, and of course, because you're on the air boundary side, this refractive index actually refers to the refractive index of air, and that is actually 1. Refractive index of air is 1. So once you plug in all the value, you realize that this is the only unknown. So do your algebra correctly and round it off to 3 or 2 SF, you will get the answer. Question 24. Question 24, I don't really need to go through, because you just refer to your book and you find that only option B is logical. The rest is out. Okay. Question 25 is again your knowledge-based question. If you have studied, should be fine. Let me see if there's anything unusual. No, it is a very common question. Okay, question 26. For me, I also find that it is quite difficult for me to understand the question just by reading it. So you have to draw it out, and you realize that it's actually a echo kind of question, because the sound wave has to travel from the wooden piece, hit the wall, and then echo back. So actually the distance that's being traveled is 2d. Okay, and the time taken for this 50 times of 2 and 4th traveling takes actually 12 seconds. So if you want to find the speed, is distance over time. So the total distance that the sound wave travel is actually 40 times 2 times 50. Total time is 12. That's why this is the answer. And what I have drawn here is actually, okay, the 1D means that the sound come out from the wooden block, so it has to travel here, bounce back from the wall. This is how the sound wave, this is the distance that the sound wave has traveled after the first bang. So when the girl hear the echo, he hit the wooden block again. So you will get this, the second D plus the second echo, and then followed by the third bang. Then keep on doing this until you reach the 50 bang. And when you reach the 50 bang, what you are hearing is actually the 50th echo. So that's why you will have the 50th. The sound waves must travel from the wooden block, bounce off from the wall, and then come back to the observer. So that's why you have the time 2 here. Okay? Okay, 27. 27, you need to know firstly that the frequency of the guitar string, what are the factors affecting it. So I would use Newton's model to explain to you. So in forces, you learn about inertia, right? So inertia is dependent on the mass. So what Newton's model is that if you have something with a higher mass, it will have a higher inertia, and if you have a higher inertia, you will be more reluctant to stay stationary, to change your state of motion. So if you want to have a higher frequency, basically you are saying that that thing will keep on vibrating at a very fast speed, and because it's vibrating, the state of motion must be changing rapidly, because it's up, down, you change the direction, right? So we are talking about high frequency, you must have a low inertia. If you want to have a low inertia, that means your mass must be lower. So in the context of a string, if you have a long string, then you will have a higher mass, lower inertia, higher mass, high inertia, and because of the high inertia, you can't vibrate that fast. So you have high inertia, low frequency. So in this case, you want high frequency. High frequency, that means you want a small inertia, which means you want a small mass, which means you want a shorter string. So that's why A is your correct option. Now in B, if you strum the string harder, what you are changing is actually the amplitude. Okay, you won't be able to get a higher frequency because the frequency is actually dependent on the inertia, how reluctant you are to change your state of motion or the direction of your motion. So strumming the string harder will only give you high amplitude. Okay, if we look at C, loosening the tension. If you loosen the tension, you would not get a high frequency. And I think you can just use a rubber band and then you just try. Okay, the reason is because when you increase the tension, what you are increasing is the left and the right force holding onto that string. Okay, so if you want a high frequency, you need to increase the tension. Okay, so in your part D, you are actually lengthening the vibrating portion of the string. Basically, you want a longer string. Okay, and a longer string give you, if you want to lengthen that vibrating motion, you are actually increasing the vibrating mass, right? So if you increase the vibrating mass, the increase of mass will give you a higher inertia. And if you have a high inertia, means that you are more reluctant to change your state of motion, which means your frequency must be lower. So that's why D is not accepted. Okay. Next, question 28 is knowledge base. Your textbook has the full detailed description of how you charge an object. Go and refer to it. They have included the explanation also. Question 29 is also knowledge base. You need to know how to draw your electric field line. So some students ask me, why not B? What if the ball is really small or the electric field here is really weak? Why can't this happen? Now the thing is that electric field line behave very similarly with magnetic field line. So for magnetic field line, if you have a magnetic material, the magnetic field line will be kind of like being drawn towards this magnetic object. Similarly for electric field line, if this thing is a conductor, the field line is going to be drawn towards it. Okay, because what happens is that if you put a conductor in between a field line, then in this conductor, it will have the induced charge here. And that's why the magnetic field line will get drawn towards that conductor. So this is highly unlikely. If this is really small, or even if the field is really weak, what you are having, it will be either curving in like that or just a straight line. Okay, the sudden change of direction here in the field line indicate that this is wrong. Okay, in a field, the field line would not suddenly have this kind of sudden change in direction. It has to be gradual change. Okay, so even if the field is really weak, this thing won't happen. Okay, even if it happens like what I drawn here, I'm not sure, can you see? Let me check the screen. Okay, you can see it will be something like that. Okay, it will be a smooth change. So that's why B is out, and A and D is definitely wrong. Okay. Okay, let's see what is this. Okay, question 30 again is it will be quite difficult if you are not strong in your mathematics. So if we look here, the y-axis is the I, that means your current is your y-axis. So what happened here is that the gradient from this 4 graph will give you actually I over V. And I over V will actually give you the 1 over R. Now how do I know I over V give me I over R? Okay, because we have to assume that this conductor is an ohmic one. So if V equals to IR, that is your standard formula. If we just rearrange the quantity, you will get R equals to V over I. So the gradient, which is I over V, must then be equals to 1 over R. Okay, so once you have this understanding, this question shouldn't be too difficult. Okay, so you have to identify a graph that is indicating a decrease in resistance when the current increase. So for those who are weaker in mathematics, what I suggest you to do is that write it down. So you have I, and this guy is going up, and your V, we don't put anything to it. Then we have 1 over R, and you want the resistance to be decreasing. So why am I doing that? Because your 1 over R, so if you have 1 over R decreasing, it means that overall this value, because the denominator is decreasing, means that the overall value of this thing will be increasing. Agree? So once you have this understanding, you can write this statement that, okay, what you want is that when your I increases, your gradient should increase as well. Okay, so with this logical deduction, you actually simplified your task. Your task is to find a graph that when the current is increasing, the gradient must be also increasing. So if you look at A, you see that the gradient is uniform, so you know that this one cannot be your answer. If you look at B, when your I is increasing, you see that actually your gradient is actually decreasing. So again, B cannot be your answer. Okay, if you look at D again, D is a uniform gradient, so it cannot be an answer. So you look at C. See, as I increases, your gradient actually increases. So that's why C is your answer. Okay?